My name is David Slowatsky, and today we will be going over taxicab geometry, what it means, a little bit of how we got to it, and some of its applications. So let's go. So imagine you are in Manhattan. A little bit zoomed in, we see that it's our beautiful city and it's full of streets and avenues. But let's be a little bit more specific. Let's say that during this time in Manhattan, you're starting at the Empire State Building and you're trying to get to the Chrysler Building. Now, can you walk in a straight line there? No, right? So here's the question. How far would that trip actually be? And how would you figure that out? Let's take a second. Okay. So, in math, we usually measure distance as a straight line. But in a city grid, we can't usually go in a straight line, right? We have to follow the streets. We can't just climb over buildings. We're not Spider-Man. So, you might want to take this route. You might want to walk down to Park Avenue and then go north from there and turn to Chrysler Building. That's one way you might do it. You might actually go a different way, right? You might want to turn a bit earlier and then turn on Lexington. So this is the idea behind taxicab geometry. So taxicab geometry was developed through Hermann Minkowski's work in non-Euclidean geometry, and that was in the early 1900s, and then later it was more popularized by Carl Menger in 1952. And the idea behind it is what we just did. Rather than measuring straight line distance, like in Euclidean geometry, taxicab geometry measures distance along horizontal and vertical paths. So it's basically like moving through Manhattan city blocks, and that is why in some may call it Manhattan distance rather than taxicab. So let's run it back a little. Okay? Like we mentioned, in math, our shortest distance is usually a straight line, and this stems from Pythagorean theorem, right? Like we see right here, if we want to go from the origin to this point right here, we basically create a little right angle triangle, and we take that horizontal difference, we square it, and we have the vertical difference, we square that, and we take the root of that sum, and we will get that distance, right? That's how we got to our formula here. However, in taxicab geometry, it is different because, like we mentioned, we can't take that shortest path. We have to go through the grid. So our distance would actually be calculated differently. If we were taxi drivers and we wanted to go from the origin to this point, we would actually use the formula d equals x2 minus x1, well, the absolute value of that, plus the absolute value of the y2 minus y1. So basically, you're adding the horizontal and the vertical movement. Okay, so let's see this difference with our ordered pairs 1, 2, and 3, 5. What is that distance? Okay, now if we were to use the Euclidean distance formula, we would calculate it like this. We select each point to be our x1 and y1, and the other point will be our y1 and y2, and our x2 and y2, and we would use our formula. So 3 minus 1, the difference, I square it, plus 5 minus 2, that difference, I square that. What I'll get is 3 minus 1, that's 2 squared, plus 5 minus 2, that's 3 squared, 2 squared is 4, plus 3 squared is 9, 4 plus 9, that's 13, and that's the square root 13. So the Euclidean distance between these 2 points is the square root of 13. And that's great if we were, again, Spider-Man. But if we were in a grid and we were driving a taxi or we would be walking, we wouldn't be able to drive this way or walk this way. So something interesting happens here. So our path might look like this, right? Our path might look like this. And honestly, in both cases, we count the same distance, right? 1, 2, 3, 4, 5. And if I go back, 1, 2, 3, 4, 5. They're both the shortest distances. So that's another concept in taxicab geometry where multiple shortest distance paths can exist. But let's use our formula that we mentioned earlier to actually measure that and see if it's correct. So, like we just mentioned, multiple shortest paths can exist. And we're going to see that by using our formula. So the distance in taxicab geometry, like we mentioned, is the absolute value of the vertical and horizontal difference, the sum of those two. So 3 minus 1, that gives me 2, right? Like we did earlier, the absolute value of 2 is still 2. Plus the vertical difference, 5 minus 2, that's 3. The absolute value of 3 is still 3. And the absolute value of 2 and 3 gives us 5. So we get 5 here too. So with Euclidean distance, we get the square root 13, which is approximately like 3.6. And with taxicab, we get 5. Meaning our distance in taxicab is actually longer. And that makes sense, right? We're not going through buildings now. So it makes sense for it to be longer. But this is only one example of how taxicab geometry changes distance. And this affects other things too. So let's see what happens. So here's another big idea. If we change how we measure distance, what happens to shapes? So let's think about circles for a second. What do we know about circles? So let's take a second. What do we know? We know that a circle is the set of all points that are the same distance from the center, right? That's basically our radius. So if this is our center, radius, 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 they're all the same distance from the center. And we also know that we are given an equation for this. It is x squared plus y squared equals r squared. But let's see if that equation actually changes in taxicab geometry. Because again, distance is different when we have a grid and we can't go diagonally. So let's use an example where we build a circle with the radius of 3. So we will need all points that are 3 spaces away from the center. And let's say our center here is the origin, right? It's easy. It is 0, 0, x is 0, and y is 0. So this is one point, right? 1, 2, 3. This is another ordered pair or point, 1, 2, 3. And again, 1, 2, 3, and 1, 2, 3. All 4 of these points are 3 units away, right? 3, 0, 0, 3, 0, negative 3, and negative 3, 0. Now, we also have these points. 2, 1, 2, negative 1, 1, 2, and negative 2, 1. Right? Let's count. 1, 2, 3. Still 3 away. 1, 2, 3. Still 3 away. 1, 2, 3. Still 3 away. These are all 3 units from the center. So here's a question. Do we already notice a pattern? What equation can we come up with that works with these points? What about these ordered pairs relate to 3? Okay? And I can even provide the extra additional ordered pairs that are all 1, 2, 3, 1, 2, 3 units away from that center. And I'll tell you, what I see is that all of these follow the equation absolute value of x plus absolute value of y equals 3, which is again our distance formula, right? The absolute value of 2 and the absolute value of -1 equals 3, right? This is very similar to the distance. It's not the distance, but it's very similar. Now, 0 plus the absolute value of 3 is also 3. That is our circle's equation. So we found our equation for a circle in taxicab geometry. Let's take this a step further. And let's connect all these ordered pairs and see what shape we actually now have. Isn't this surprising? What we have here now is not a circle, but rather a square rotated like a diamond. All of these points are 3 units away from the center. And honestly, this still follows the definition of a circle, right? All of these points are still in the same distance from the center. Nothing about the definition of a circle says it has to be round. The only thing that changed here is how we measure distance. And the interesting thing is that this actually extends to all the other shapes. So let's look at a few more. Below here, we have other shapes that will be round in Euclidean geometry, but now when we're discussing taxicab geometry, so an ellipse, for example, is all the points where the sum of distances to 2 points stay constant. But if we use taxicab distance instead, that shape does not look like a smooth oval anymore. It becomes more like a polygon. So again, what changed is how we measure distance. And that completely changes the shapes. Okay, so the last point is, okay, you're telling us all this, but why does that matter? So in this geometry, we can use these circles to measure distance in different situations. So for example, if you're this taxi here, and the 7 line is here, right? You're in Flushing. We can find the shortest distance from that point to the line by expanding that taxicab circle outward until it touches the line. Because distance is defined differently, the result depends on the shape and direction of that path. So this is actually what I learned as an undergrad learning computer science. When you open up Google Maps and it tells you that shortest path, that is the idea of Dijkstra's algorithm, which is an algorithm to find the shortest distance. It will keep expanding in each direction, until you get to your destination. And it checks what's that shortest path. So it will go here, here, and here, and see how long that will take. Of course, it counts for other things like traffic, and using that, it will tell you that shortest distance. And like it says here, the GPS and navigation systems, like I just mentioned, use it. City planners use this distance, right, to make sure that stores are near other places. Robotics use them. The robots use it to calculate paths. The computer science pathfinding, Dijkstra is only one algorithm of many that use this to calculate distance. And of course, other grid-based movement systems. So that's really it. Very interesting topic to me. Here are my references. And yeah, that's it. I hope you enjoyed this lesson, and have a great day.